let me phrase this in terms of what we actually know. That's one number we know for sure, which is actually the dark matter density in the solar neighborhood. And that's purely from dynamical measurements. And that gives us this number, which is a well-known number. It's about 0.3 GeV per centimeter cube. That's the mass density in the solar neighborhood. So that number for sure we know, and it's from astronomical measurements. And one interesting question one could ask is the following. In this vast spectrum of possible dark matter particle masses, can we at least identify one characteristic mass? And one way we can identify is to use this number, this 0.3 GeV per centimeter cube. And now I'm going to show you kind of a cartoon picture where I draw down a sphere with basically the green particles represent the dark matter particles. And the radius of this sphere is the de Broglie wavelength associated with these particles. And let's ask ourselves the questions, the following questions. What would it take for the de Broglie wavelength to exceed the typical interparticle distance? So the situation would be like what is depicted in this cartoon, meaning within a de Broglie sphere, there would be multiple particles instead of actually having just one particle. What would be the defining particle mass where that happens? As you can imagine, when you make the dark matter particle mass smaller and smaller, the de Broglie sphere becomes bigger and bigger. So at some point, it would start to exceed the interparticle separation, given the known mass density in the solar neighborhood. And that defining mass is actually kind of well known, is about 100 electron volts. And in this talk, we will be interested in the regime where the dark matter particle mass is less than this number. And I call it the wave regime because this is a regime where, because there are multiple particles, in fact, at the very light end, many particles. For example, if you go to all the way to 10 to the minus 22 electron volt, for example, the number of particles within the de Broglie volume is like 10 to the 90 or something like that. It's a huge number. In this kind of regime, it's actually useful and practical to think of it not so much as a collection of particles anymore, but a collection of waves. And in this talk, we want to basically explore this regime, basically the wave regime. And to give you kind of a concrete idea, I list basically a few sample numbers, right? So the de Broglie wavelength, if the particle were the extremely light one, 10 to the minus 22 electron volt, would be 100 parsec. The de Broglie wavelength is basically astronomical. And as you could imagine, if the particle were this light, then there would be astrophysical implications, which we will talk about. On the other hand, a lot of attention and experimental efforts, particularly on detecting the QCD axion, focus on mass that is light, but not that extreme light. So it's 10 to the minus 6 electron volt, for example. The ADMX experiment, that's basically the mass range it focuses on. The de Broglie wavelength would be 10 to the 4 centimeter. You are still in the wave regime, but the de Broglie wavelength is not astronomical, but it's still large enough that there are interesting implications for experiments that I want to talk about. So in this talk, essentially my focus is on the wave phenomenon, and keep in mind kind of two canonical masses. One I would call ultralight, 10 to the minus 22. The other I would just call light, 10 to the minus 6. And the manifestations will be different. Some in the ultralight regime, there will be astrophysical implications. In the merely light regime, light 10 to the minus 6, there would be experimental implications, basically of this wave phenomenon. And by wave, I also want to emphasize here, basically we are talking about classical waves. In other words, think about kind of the analog with E&M. So we are in a regime where you have many photons, and as we all know, there are many situations in which classical waves or classical Maxwell equations is a very good description of what's going on. And that's basically what we have in mind. Okay, so this is the wave regime we have in mind. It's a classical wave regime. So this is the outline for the talk. I want to start with just fairly briefly on the particle physics motivations, why we might want to think about light dark matter. And then I think probably a fair fraction of the talk, I will be talking about just the dynamics. How do we think about the wave dynamics? How do we think about the phenomenology? And then I will close with astrophysical implications for the ultralight dark matter and experimental implications for light dark matter. And once again, the canonical masses are 10 to the minus 6, 10 to the minus 22, although there's really a whole range. Keep that in mind as we go along. The ultralight version, by the way, is often called fuzzy dark matter. The name was given by the list of authors given here, Huber, Kana, and Gruzinov. So let me start with the particle physics motivations. And again, please do interrupt me as we go along. I think it will work better that way. So particle physics motivations. A fairly natural candidate for a light particle. And in this talk, I'll mainly focus on the light scalar particle. This, of course, is some sort of a pseudo-Nambu-Goldstone boson. As you know, a Nambu-Goldstone boson would be strictly massless. And the term pseudo-Nambu-Goldstone boson refers to the fact that what we have is a case where the particle acquires a mass from non-perturbative effects. So at a perturbative level, it should be strictly massless, it's shift symmetric. But at a non-perturbative level, you generate a small mass from non-perturbative effects, such as from instantons. And here I show you a picture just to remind ourselves how that works. I'm sure it's familiar to most of you. This is the Mexican head potential. And the axion direction is basically the U1 direction that go around the Mexican head potential. And the Mexican potential, if you look at the picture closely, is even a little bit tilted, which means there is a small potential. This angular direction, so to speak, is not exactly flat. There's a small mass, there's a small potential. And the most well-motivated example of this, the most well-explored, is the QCD axion, which was motivated by the strong CP problem. And this is a long history, and I'm not going to go into that history. We don't have time for that. And again, I'm going to assume this is well known to most of you, so I'm not going to go into that history in detail. I should also mention that there is, of course, a whole kind of plethora of axion-like particles, usually called ALP, in string theory, which are not necessarily the QCD axion, although it could include the QCD axion. And these axion-like particles, they generally come from compactification, meaning you have Kaluza-Klein modes of higher form fields in a scenario where you have compactified dimensions. And some of those excitations behave like axions. So these are called axion-like particles. And again, there's a long history of papers in the literature that consider this. Now, let me now switch focus a little bit. I'm going to, in the next slide, focus on the particular example of the ultralight version. The QCD axion is going to be a little bit different, although the story, there is some similarity, as I'll explain. So the next slide is kind of the motivation, in particular, for the ultralight version one. And by ultralight version, I mean around 10 to the minus 22 electron volt. Although if you follow my argument, which I'm going to explain on this slide, there is really a range. It's not quite exactly 10 to the minus 22. In fact, that could be a rather large range as well. So the argument goes something like this, and it's essentially an argument based on thinking about relic abundance from the Big Bang. So again, here I show the Lagrangian. So you have phi, that's the axion field. Think of phi as basically an angular field, right? Like in the Mexican head potential, it's the angular direction. And as an angular field, there is actually a periodicity scale. If it's dimensional angle, of course, there's just 2 pi. Phi for us is a field with mass dimension 1. So the periodicity scale we are going to call capital F here on this slide. Very often this F is called the axion decay constant, although for our purpose, exactly what it has to do with axion decay is not so important. It's just a scale. And if this were strictly Navier-Goldstone boson, the potential should not exist. So the lambda 4th term should not exist. It should just be strictly shift symmetric, a massless scalar. Again, very often non-perturbative effects such as from instanton would generate a potential that looks like what you have at that Lagrangian, the lambda 4th term, where the shift symmetry for phi is now broken down into a discrete symmetry, where phi, if you go around by basically f or 2 pi f, then you have the potential come back to itself. So it has this cosine form. For QCD axion, the potentials still have this discrete symmetry, but it's a little bit more complicated. But nonetheless, the lesson remains, which is the following. If you take this potential and you expand out in small phi compared to f, and you, from the quadratic term, you can read off the mass of the axion, and the mass is given by the expression shown on the slide, would be of the order of lambda squared over f. And once again, there are many candidates of this sort in string theory, for example, and it has been discussed a lot in the literature. Now, let me move on to why, in particular, it's interesting to think about an extremely small mass. Keep in mind that the non-perturbative effects is generally suppressed by a moderate action, the instanton action, and because it's exponentially suppressed, it's not hard to imagine the instanton action. It need not be too big, let's say 100 or something like that. And it would give rise to a lambda effectively that's exponentially suppressed. So it's a very small lambda and therefore a very small mass. And in particular, a very small mass seems to be appealing in the following scenario. The mechanism is called misalignment mechanism. Again, it's very well known. And what I do here, I'm actually a question for you. Can you see my cursor if I move the cursor around on the slide? Can someone tell me?
Yes.
You can, okay, great. So I'm going to use my cursor as the pointer, right? So I have the potential like so here, this is the potential. This potential is supposed to represent basically this cosine potential up here, okay? And the span of this potential is that periodicity scale F. In the early universe, the expansion of the rate of the universe is so high that essentially the scalar field is frozen. Basically, Hubble friction causes the scalar field to be frozen at whatever primordial value it had, okay? And here is going to be our assumption number 1. We are going to assume the scalar field, this phi, the axion, initially, the primordial value is of the order of the periodicity scale itself, F, or the axion decay constant. Now, this is an assumption. It need not be that, but it seems a very natural one, given that F is the only scale in the problem. By the way, this assumption is often not called, basically expressed in a different way. People would say the misalignment angle is order 1, meaning phi over F is order 1. And let's take that as an assumption. That's our starting point. Now, as the universe expands, the Hubble expansion rate is going to drop. And at some point, it's going to drop when the Hubble expansion rate reaches basically m, the mass scale of the axion. At that point, the scalar field will start rolling down the potential and start to oscillate. And as the universe expands, the oscillation is going to get redshifted. So energy is going to be sucked out of the oscillations. So the oscillation amplitude gets smaller and smaller. And basically the scalar field would just be oscillating fairly close to the minimum. And at that point, basically, you can even forget about this whole cosine potential. You can really treat this as an m squared phi squared potential since you are oscillating so close to the minimum. And it can be shown fairly easily. The energy density in the oscillations would redshift just like matter. It would redshift like 1 over the scale factor cube. And if you follow basically this whole reasoning, in fact, you can calculate what is the leftover energy density today. And skipping the math, you would find basically the expression given here on the slide, omega in matter, or in this axion matter, would be of the order of what is necessary to explain, to account for dark matter, the known dark matter abundance. If you make two assumptions, one assumption is that the axion decay constant is of the order of 10 to the 17 GeV. It's a rather high number. It's somewhere basically around gut scale or between gut scale and Planck scale. That seems to be, again, fairly generic in these string theory scenarios. So that's one motivation for picking this number, although you don't have to pick this number. And then the other number that I pick here is the mass of the axion, and it's a very light mass, 10 to the minus 22 electron volts. And it turns out for this light mass, you basically fairly easily get the correct radical abundance. I should say this calculation really mirrors what is known in the QCD axion literature. The only difference really is that in this calculation, the potential is just assumed fixed. In other words, the mass associated with the potential is just a constant. In the case of QCD axion, as you know, the axion really does not acquire mass until confinement happens. And so it's a temperature dependent potential. So the calculation is more complicated. But nonetheless, it's really just the classic calculation, basically done by this set of authors, but assuming a rather simple or simple-minded scenario where the potential is just constant. I should emphasize, if you follow this reasoning, the radical abundance is in fact more sensitive to your assumption about F than your assumption about M, right? It goes like F squared, M to the 1/2. Therefore, it should be kept in mind that all you need is to order F a little bit, then to explain to account for the observed dark matter abundance, your M would have to change a lot. So really there is a very large range in mass. Nonetheless, this argument based on radical abundance does suggest that maybe we should think about a dark matter particle that's rather light. So that's kind of the take-home message. And let's explore the consequences. And in particular, 10 to the minus 22, again, is what I call the ultralight version. In the rest of this talk, I would freely span basically from 10 to the minus 22 all the way to 10 to the minus 6, or even higher. As long as we are in the wave regime, most of what I'm going to say applies, okay? So this actually concludes what I have to say about the particle physics motivation.
Can I ask you something? So
please do.
Assuming that dark matter is, I mean, 10 to the minus 22, you're saying that is somewhat more motivated than other values. So is there a reason why the smallest galaxies, they have a size that corresponds to this wavelength, or is it accidental?
That's a very good question. I mean, historically, I would say the fuzzy dark matter, basically this paper by Huber, Cannon, and Gruzhinov, they introduced 10 to the minus 22 precisely because of the smaller size of galaxies. So that number was introduced by them basically based on astrophysical motivations. This argument based on radical abundance, I'm not quite sure who actually first formulated it. I think it's probably widely known in the community for among people who have thought about this, that if you assume an axion decay constant that's gut scale, following this misalignment mechanism, you actually you actually do prefer a fairly light mass. Now, why these two arguments happen to coincide? Is that pure coincidence? I don't know. I'm open-minded about that. Some people might take it as a suggestion that maybe this is a hint from nature, but I'm pretty open-minded about that. Yeah. So the short answer to you, Michele, was it Michele who asked the question?
Yes.
Yeah. So the short answer is probably a coincidence, but we don't know. Okay. There's no fundamental reason why the two have to give you the same answer. Okay. So other questions before I move on to the next kind of set of points? All right, so I'm going to move on. So let's talk a little bit about the dynamics. And it's important we understand the dynamics. And fortunately, the dynamics is so simple that it basically fits within one slide, right? So the first equation is, of course, the Klein-Gordon equation. And again, we have the Klein-Gordon equation because our axion is oscillating very close to the minimum of the potential, as we discussed before, right? So if I step back to the previous slides, sorry about that, previous slide, this slide, our oscillation is fairly close to the minimum, and therefore we can just ignore self-interactions, because if you expand the cosine, of course, beyond the quadratic term, the next order term would be the quartic term, lambda 5/4. And that term, in some cases, could be important. For most of what we have to say is actually not important, and so we are just going to ignore it. Although at the end, we might come back to it. So from now on, I'm going to just ignore self-interactions. For example, the lambda 5/4, all we have is basically the classic Klein-Gordon equation. We are interested in application in the non-relativistic regime. For example, the velocity dispersion in the Milky Way halo, for example, we know is basically 200 kilometers per second. So it's nowhere near the speed of light. So the non-relativistic approximation should work pretty well. And it's a fairly standard trick, as you know, that is convenient to introduce a complex scalar called psi here. And rewrite basically the real scalar, the Klein-Gordon scalar, the axion phi, by basically factoring out the primary time dependence e to the IMT, which is just the frequency of that oscillation. Psi is a complex scalar, and it has both space and time dependence. And the assumption here is that whatever time dependence psi has is a lot slower than m. That's basically the non-relativistic assumption. And if you go through the math, again, it's a very standard thing. You would get from Klein-Gordon the Schrödinger equation. So psi plays the role of the wave function. And here I even included the single interaction that is actually important in this problem, which is gravitational interaction. So capital phi is the gravitational potential. So basically what you should keep in mind, and I should have written that down actually, there are basically only two equations that you need to think about for our application. One is the Schrödinger equation. The other is the Poisson's equation that tells you that psi square, which is basically the density, sources the gravitational potential, which is basically this capital phi. Those are the only two equations you need. And let me also emphasize, and it's important point to make again, that what we are talking about here is a classical field theory. In other words, despite the appearance of the wave function psi, and I'm going to continue to call it the wave function, this wave function psi should be thought of as a classical scalar. And the reason, again, is what I said earlier. We are in a regime where there's very high occupancy. We have a large number of particles in the de Broglie volume. And in that regime, really, classical dynamics is a very good description of what's going on. The quantum fluctuations are very small and negligible. And so we are going to use the Schrödinger equation this way. and where psi is sort of as a classical scalar. Now, let me also emphasize, of course, the Schrödinger equation, of course, famously has a symmetry, which is a U1 symmetry, basically rotating psi by a phase. And that, as you know, leads to the conservation of probability in quantum mechanics. Here, again, interpreted as a classical theory, this is just conservation of particle number, which actually should not surprise us because we are in the non-relativistic regime where the axion particles, they are not being created or destroyed. And so there is particle number conservation. And that is encoded in the U1 symmetry of the wave function psi. Okay, so I hope all that is familiar to you. There is an alternative viewpoint which is actually useful for understanding. So let me present that to you. The alternative viewpoint is to think of psi as describing a classical fluid of some sort. And the way you rewrite this complex variable psi is in terms of an amplitude and a phase. The amplitude, if you think about it, ought to be associated with the square root of the density, right? Because the density is naturally associated with psi square anyway. So square root of density is basically the amplitude of this wave function. The phase turns out should be associated with a velocity potential, basically like what I wrote here. The velocity goes like the gradient of the phase. If you do this kind of split, basically rewrite the wave function in terms of the amplitude and the phase, then what I talk about particle number conservation or mass conservation is now actually written in a way that's very familiar looking in fluid mechanics. This is how mass conservation actually looks like in fluid mechanics. And of course, the Schrödinger equation is a complex equation, so we have two independent equations. And therefore, besides mass conservation, there ought to be a second equation in the fluid picture. And the second equation is the next equation, the Euler equation, which again looks very familiar. The left-hand side is basically the Lagrangian derivative of the velocity. It's basically acceleration if you want. The acceleration of a fluid element goes like, of course, the force, or the which is basically the gradient of the gravitational potential. That's the gravitational force. In addition, there's this maybe to some of you a weird looking term, and this is basically often called quantum pressure. Although in the context of what we are discussing, it's a little bit of a misnomer for two reasons. One is that this term actually is not a pressure. If you actually recall fluid mechanics, this actually is more like the gradient of the stress. And the stress you can actually show in this kind of fluid has off-diagonal components. And it's precisely this tensor structure that gives you this term. And so this is not really pressure. This is some form. This arises from some form of stress, if you want. And second of all, as I discussed earlier, we are not really dealing with a quantum mechanical system. In other words, you notice here I'm being lazy and everywhere drop h bar. But if you ask where the h bar, where does the h bar goes? Essentially, h bar goes wherever you see an m. Yeah, wherever you see an m, what we have done is in fact replace m over h bar, but just by m. That's the only place where h bar shows up. And if you want 1 over m, define a length scale. Okay, and as far as we are concerned, once that length scale is given, all I have is a classical system of equations. And this, let me also emphasize, you notice the velocity is a gradient flow, it's a pure gradient flow. So it certainly resembles what we know about superfluid. So one could think of this as a superfluid. And this is really all we need to know about the dynamics. Let me pause here in case there are any questions about the basic dynamics. All right, very good. So here I'm just quoting Feynman. you can actually find a discussion of this sort of issue. This volume 3 of Feynman lectures, the last chapter in that book you might recall. And I actually highlighted here that psi is the wave function for each of an enormous number of particles which are all in the same state. So psi star, which is what we call rho, basically, or rho divided by m, can be interpreted as the density of particles. That's basically what I said earlier about how to interpret this wave function. And by the way, this Euler equation with the funny quantum pressure, you can also find in the same chapter in the Feynman lectures. It's a very well-known thing. So this is again that set of equations, just to remind you. Now, most of what I want to talk about in the rest of the talk has to do with the following: the fact that we have a superposition of waves. And here I want to actually make it visual. So here I show you a cosmological simulation. This is a simulation done by Xin Yu, I think, who is actually joining us in this seminar. And what I'm showing you is the following. Imagine in that dark matter is indeed some light dark matter, like fuzzy dark matter, for example. In the early universe, we start with the usual Gaussian random initial conditions. So the universe is more or less homogeneous with small perturbations on top. And as the universe evolves, gravitational instability causes these perturbations to grow. And eventually you have collapsed into filaments and halos. And what I want to show you now is not a movie in time. This is just one snapshot in time in the late universe. But the movie I'm actually going to play in a moment is taking a snapshot at late time and just cutting across slices, just to show you the three-dimensional structure. And let me play the movie now. I hope it works. Complain to me if the movie doesn't play, okay? Are you able to see the movie?
Yes.
Great. So again, just to reiterate, this is not a movie in time. This is just a movie in space, taking a box at late time and just slicing across different slices in a three-dimensional box. It's just to show you the three-dimensional pattern. But I hope actually one thing very distinctive, which you can actually see even in this very last slice, is that you see wave interference, and is an inevitable kind of consequence of what you have in the wave regime, right? Remember in this slide, what I'm showing you, the color coding tells you density, right? And remember, density goes like wave square. And suppose now you have a random superposition of waves, then you are going to have destructive and constructive interference. And these interference fringes show up basically in this picture, both along filaments and basically in halos. In particular, you see both constructive and destructive interference, right? The destructive interference are places where in this color coding is particularly dark, yeah? Meaning the density actually goes really low. And in fact, that's actually what I want to focus on in this talk, is actually these locations where you have destructive interference, in fact, very severe destructive interference. I should also say, to give proper credit, this kind of picture that you have interference effects in this kind of wave regime was first shown in a very nice paper by this group of people, and later on followed by actually many groups who do this kind of simulations. Okay, so I'm now going to the next slide. There are many effects that one could talk about in terms of wave effects, and I give you a partial list here. many of these, well, some fraction of these are discussed in our work back in a few years ago. What I want to do today is not so much to talk about them, although if you ask me at the end, I will be happy to talk about any of them. I want to focus on something that's relatively recent that we have been thinking about and work on. In particular, the possibility of vortices and more generally walls, domain walls, or if you want, topological defects. If I have time, I would also talk about a different kind of signature which has to do with black hole hair, although I rather suspect I might not have time for that. So let me focus on vortices, right? So next slide, vortices. At first sight, it seems like a very, not a very promising thing to think about, because remember the fluid formulation, right? The fluid formulation tells us the wave function has a phase theta, and the phase theta is basically velocity potential. So the velocity looks like it's pure gradient flow. So how could you even have vortices? Vortices, remember, are places where the curl of velocity is non-zero. And if the velocity is pure gradient, the curl by definition is just zero. So at first sight, it seems, you know, it's kind of a trivial question. Of course, there are no vortices. There is a loophole in this argument, as you might imagine. And the loophole essentially comes from the fact that, well, think about the places where the density actually vanish, okay? In those places where the amplitude of the wave function vanishes, the phase actually becomes ill-defined. And it turns out those are precisely the places where vorticity is allowed. Because the phase is ill-defined, if you want, the velocity is ill-defined. The quantum pressure, by the way, is also ill-defined. Rho is in the denominator. So something about the fluid formulation, if you want, breaks down precisely at those places. So that's what I want to talk about. I also want to motivate this a little bit better by saying, you know, your first reaction might be, okay, yes, this description breaks down when the density vanishes, but you might reasonably ask, you know, how often does this happen anyway? Isn't this something that's very unlikely to happen? You know, in this picture where I have random superposition of waves, where disruptive interference happens, the natural response would be to say, okay, you might have some partial disruptive interference, but how likely you have complete disruptive interference so that rho actually go all the way to zero? I have to confess, before we started thinking about this problem, we also thought this is very unlikely, but I will also show you, and this will come up later in the talk, maybe in 10 minutes or so. That turns out this is ubiquitous, meaning this actually happens much more often than you think. So for now, let's postpone that question of how often does it happen. Let's just assume it happens somewhere, just chance disruptive interference, create regions where the density go all the way zero, and let's just think about what happens around these regions. So that's going to be my focus for the next 5-10 minutes. Let's just think about what happens around these regions, in the neighborhood of these regions. Okay. Before we do that, though, I want to again emphasize. Let's step back to this movie. Sorry about that. So actually, this is good enough. So if you think about again this simulation that I showed you, in the early universe, when the density is roughly homogeneous and there are only small fluctuations, 10 to the -5 on top, you clearly cannot have total disruptive interference, right? The disruptive interference can at most basically take the density a little bit lower, but not all the way to zero, because the fluctuation is 10 to the -5. To have complete disruptive interference, you definitely need gravity to do the work, to amplify the perturbations until they become order 1. And then when you superimpose these order 1 fluctuations, these waves, then in some cases, you could have disruptive interference that takes the density all the way to zero. So vortices in this picture has to emerge with the work of gravity. It did not exist. This complete destructive interference did not exist in the early universe. Only in the nonlinear regime would you produce them. So I want you to keep that in mind. And so now let me start with the following. Let's think about now a place where the wave function, just by chance, okay, for now, let's not postpone the question of how often it happens. Let's say it happens somewhere, that the wave function vanishes at a location which I call the origin, at x equals 0. And to make the argument as simple as possible, I'm going to focus at first in one spatial dimension, 1D. And as I will argue now, there's a way to think about what happens in the neighborhood of the origin, where the wave function vanishes, where it's fairly obvious what you have is a domain wall. Okay, so I'm going to give that argument to you. And in some sense, it's such a simple point. It's actually very easy to miss. So I apologize if I'm being pedantic here. So consider psi, the wave function, in one spatial dimension. And imagine x is the coordinate of that spatial dimension. And at the origin, once again, x equals 0, the wave function vanishes. So I cross it out. Let's imagine doing a Taylor expansion around the origin. If I do a Taylor expansion, of course, the next term would be the first gradient of psi, evaluated of the origin, times x, okay? And now I'm going to make kind of the first assumption. Generically, if this is something that occurs by random chance, it's probably okay to assume the first gradient does not vanish. So I'm going to go ahead and assume that. And therefore, in the neighborhood of the origin, the wave function is just dominated by this linear term. And now let's think about what this linear term means. Once again, it's a very simple point, really, but there is an important message here. I apologize for being pedantic. So I'm going to draw this figure, which is the real and the imaginary part of psi, yeah? And imagine I dial x from, let's say, negative value, crosses the origin to positive values, okay? And here I denote this gradient, first gradient of psi, using this blue vector. Again, remember psi is a complex quantity, has two components, real and imaginary part. So its first gradient is kind of a vector, it's a vector in this plane. And imagine I march along from negative x to positive x. And what happens to psi? Well, psi clearly would just march along this arrow, right? Would it not? So it would go from basically this quadrant vanishes at x equals 0 and then emerge on the other side. Very simple. But now, if I ask you what happens to the phase? Well, it's clear the phase has a jump because the phase originally is on this side. Now it flipped over on that side. From negative x to positive x, crossing x equals 0, the phase has a pi jump. And if I plot the phase, it basically pictorial looks like this. You see a jump. And this is, of course, just a very simple example of a domain wall. This is a case where looking at the phase, it's fairly obvious you have some kind of discontinuity, and the discontinuity is just this jump in the phase, exactly where the wave function vanishes. This is what happens in one dimension. And I hope it's relatively easy to understand.
Lam?
Yeah, please.
I have a question. But however, here, the modulus, the absolute value of the field is vanishing, right? So in order to have a domain wall, you need to have some energy localized at the domain wall in order to be a physical object. If the modulus vanishes, I would suspect that essentially this is unphysical, no?
Unphysical in what sense?
In the sense that there is not a finite amount of energy per unit length localized there.
Yeah, this is a very different kind of defect. If you want, even though the argument is topological, this object is not really protected by topology. As you will see, these objects, they could form and they could also disappear. So I think what you call unphysical is in that sense. These are things that can come and go, but these are things that can certainly form. So to the extent that they can form, I would say it's physical. But they are very different from the more familiar topological defects that we are familiar with, where there's usually some kind of potential associated with your field, and the potential basically causes a localization of energy density where the defect is, which is basically the wall energy density, like what you're referring to. So I agree with you, yes and no. It's unphysical in the sense that it's unfamiliar and it's not protected, so to speak, because they can form and disappear. But it's physical because they actually could happen. And in fact, I want to show you that they actually form very generically.
Okay, thanks.
Yeah, thanks for asking. Thanks for asking. I mean, this argument is so simple. As you can see, this is really just a Taylor series argument. In fact, I've not made much assumption about how this scalar field interacts even, right? This is purely just a Taylor expansion argument around the point where the wave function just by chance happens to vanish. Of course, the precise structure as you go further away is going to care about the interactions. And we will talk about that as well. Yeah. So this is a wall defect in one dimension. Now let's go to higher dimension. So I'm going to add the following. This argument you can generalize to higher dimensions. And generalize to higher dimensions how? So let me talk about it like this, right? So remember the defect requires the wave function to vanish. And the wave function has really two components, real and imaginary part. So it requires the vanishing of two things at the same time. And let's specialize to the case of three spatial dimensions, which is relevant for what we want to discuss anyway. In three spatial dimensions, let's ask, well, what are the points where both components of the wave function vanishes? Think about it this way. In three spatial dimensions, if I ask you, what describe the set of points where, let's say, the real part of the wave function vanishes? You will probably say, well, it's some kind of surface, right? And if I ask you what is the set of points where the imaginary part of the wave function vanishes in three dimensions, it would be another surface. And if I ask what are the set of points where both happens, well, it will be the intersection of those two surfaces. So therefore, it actually forms a line, yeah? And so just based on this argument alone, generically, what you expect is a defect that has basically the shape of a line, is a one-dimensional defect. And again, kind of a continuity argument tells you this line cannot end. So in fact, in three dimensions, this line has to wrap around and close upon itself. So this is what actually we would call a vortex ring. So it's a ring. And if I look at what happens close to a ring, and so in this cartoon, I draw basically a segment of that ring. This line, the purple line, is that vortex line, is one segment of a ring. And if I basically follow exactly the same argument that I did for the domain wall, and I ask, what happens to the phase as I go around in a loop around this vortex line where the wave function vanishes? You can fairly easily convince yourself that the phase of the wave function must wrap around. And basically it wrap around by basically integers of 2 pi. And again, the argument is really very similar. You do a Taylor expansion argument like what I did before. At the origin, for example, some point along this line, the wave function vanishes. Assuming the first gradient doesn't vanish, you have the first order term dominating in the neighborhood of the vortex. And then you just have to basically follow the same set of arguments and show that the phase has to wrap around. In general, it wraps around by 2 pi or integers of 2 pi. It turns out you can show as long as this first order term does not vanish, it will wrap around by 2 pi. If by some coincidence, the first term actually vanishes, you have to go to a higher order in the Taylor expansion. then those will give you higher winding in 2 pi. And as we will see in a few minutes, when I show you actual simulations, because these defects, they form basically just by random chance destructive interference, the probability that you actually have higher winding is actually fairly small, meaning generically, the first gradient does not vanish. So it's a very generic thing that you should expect just single winding by 2 pi. If you go to the fluid picture, what it tells you is that the velocity, which is the gradient of the phase, if you integrate around a loop, this is called circulation. It has this characteristic form, which is integer of 2 pi. There is a scale, of course, and the scale is basically given by the mass of this light axion, essentially. That is the velocity circulation. And you actually get even more out of this Taylor expansion argument. You can see the Taylor expansion argument tells you that close to the defect, the wave functions should scale linearly with separation from the vortex, which means the density, which is the wave function square, should go like separation square. So that's why rho goes like r square if n is equal to 1, if it's integer winding. Again, if you have a higher winding, that it goes like r to the 2n. But generically for us, n is 1. So density goes like r squared. And furthermore, because of this kind of topological constraint, the velocity circulation is actually equal to a fixed number. You can also see that as I go around a circle that is bigger and bigger, this length, of course, grows with radius. So it basically tells you velocity must go like 1 over radius, like so here. Okay, so the velocity grow and grow as you get closer and closer to the vortex. Probably you should not get too close. At some point, you will be getting to what we would call the Compton scale, not the de Broglie scale, at which point probably you should not use the non-relativistic description. But nonetheless, the velocity grow and grow. So these are kind of two very characteristic predictions out of this kind of very simple-minded, really, Taylor expansion argument. And again, I want to emphasize in this argument, we are not really making a whole lot of assumptions about how this scalar field interacts. It's pure Taylor expansion argument close to a point where a defect happens to be. And for those of you who think about axion strings, I want to emphasize what I'm talking about here is not the familiar axion strings. So the familiar axion strings are the strings where the relevant U1 is the Petri-Queen U1. Here, the relevant U1 is purely this U1 associated with particle number conservation. So these are very different kind of objects, okay? Let me pause here in case there are any questions.
Sorry, Lam, by the way, how much time do you think you have?
Can you actually tell me how much time do I have?
So now it would be 1 hour. So
oh, it's already 1 hour. Yeah. Oh, I see. So
yeah.
I've been going way too slow. So tell me how much time do I have? Should I wrap up in
10 minutes?
In 10 minutes? Okay. Yeah. So I'm going to try to go faster. I'm going to skip some of the slides, but really the main point are actually in this slide that I just talked about. Those are the main points. Okay. So now I'm going to show you. I think I'm going to show you the snapshot from a simulation. So this is one snapshot from a simulation. This is the interior of a halo that forms from cosmological initial condition under gravity. And in this snapshot, basically in the middle, you see kind of a ring structure. The blue indicates the density is very low. And this would be maybe a candidate vortex ring. However, you probably should not believe me just based on this, because as you can imagine numerically, the density is never strictly 0. At best, you can say this is suggestive of a ring, but the density is just small. It's not literally 0. The way you actually check this is an actual ring is to actually check the phase. So if you flip this ring around and go around and check whether the phase winds around, that's how you know you have a vortex ring. And that's what the next snapshot is supposed to show, although it's probably hard for you to see. I've flipped the ring basically by 90 degrees, and the way the phase wraps around, basically on this side and that side, that is the circulation that we are looking for. And this is just one example. This is a cartoon that shows you how a vortex ring actually works. If you have a vortex ring, and the circulation goes like this, and in fact, the ring as a whole would actually move with a velocity that goes like 1 over the radius of the ring. And once you know these things are there, it is possible to write algorithms that just identify them in a halo. So this is one particularly nice example is the merger of I think 4 halos that form vortex rings, highlighted here. The halo is basically a fair fraction of this box. This is a particularly symmetric configuration. That's why the vortex ring looks so nice. In practice, they are much more messy. This is a more messy initial conditions, the merger of several small halos. And one can check whether this prediction works out. For example, the density profile around a vortex, does it go like separation square? And these are basically several vortices. And indeed they do, as long as you're not too far away from the vortices. You can actually also check the velocity profile. The velocity drops like 1 over distance, like what I talked about. This is a 2-dimensional simulation. Let me just skip this. Once you know actually these things are possible, in fact, it's very nice to study them just by generating a superposition of waves with random phases. And this is an example of that. And I'm going to skip this. You can even think about how vortices, what do they do when they intersect and so on. This is just that movie. Unfortunately, I don't have time to go into that in detail. You can ask me at the end. I'm going to skip this as well. Let me make some comments. So this is my comment number 1. Should defects be rare? Naively, one might think yes, but in fact, it's not. You expect on average 1 vortex ring per de Broglie volume. And in particular, especially in 2 dimensions, you can compute this analytically. For a halo, which is composed of a superposition of waves with random phases. And essentially, you'll be doing the classic calculation of what people call zero crossing, where the wave function crosses 0. And it turns out, generically, you would have 1 crossing per de Broglie, per de Broglie block, basically. So it's a very generic thing. One interesting outcome of all this is that small rings move faster, or a segment of ring that are particularly curved, they will move faster. The curvature scale is basically this R. So the smaller R is, the faster it moves. You might wonder connections about angular momentum. Just very briefly, these simulations that we did coming from the collapse of a halo, those halos have no net angular momentum overall. So despite that, vortices form anyhow. So it appears vortices, the formation does not even require angular momentum. It's pure chance destructive interference. And having angular momentum also does not by itself imply the existence of vortices. I don't have time to go over that point, but ask me towards the end if you are interested in that. Let me skip ahead. We can measure the distribution of ring size. This is the distribution. It's an exponential distribution. The length scale, which is the only length scale in the problem, is the de Broglie wavelength. This slide is interesting once we actually go to implications for experiments. This is the probability, the 1-point probability distribution of the magnitude of psi. And if you do a random phase model, which is purely analytic with a Gaussian velocity dispersion, this is the dashed line that we will predict. And I want to highlight in particular this peak at basically when psi is 0, this is basically the sign of having a lot of destructive interference. If you compare that with simulations from gravity, the actual collapse of a halo, this is the solid line. So the random phase model works pretty well in describing what happens close to when you have basically mild or moderate psi. It does not describe very well what goes on when you have very large overdensity. We can talk about that towards the end. So let me talk about, I'm going to finish with some thoughts on observational and experimental signatures. And I'm going to, due to the lack of time, I'm going to skip this one. This is basically has to do with how a vortex, if we transit over a distant source, would cause basically change in the position of the source. In the end, the effect is very small. So let me not focus on that. Let me focus on a case where it looks like the effect is actually observable and might even have been observed. And what I show here is a situation where you have basically very strong magnification. Here, what I show, this line, the purple line, is called the critical line. And essentially, this is a place where the magnification, if your source is in the right place behind a lens, the lens could be a cluster of galaxies or a galaxy, that if your source is the right place, your image would show up along the critical line with infinite magnification formally. But if it's slightly off, then you will have two images, one on each side, and the two images would be very highly magnified. And in general, it turns out you can actually show in cases where the magnification is very high, people have observed magnification as high as 100 or even higher. Generically, these two images should have the same magnification. However, if there is substructure on the scale that's smaller than the image separation, such as from this interference substructures, this constructive and destructive interference substructure, it would cause these two images to have slightly different magnification at the level of 10%. That's our estimate. And such an effect, by the way, in the literature is called flux anomaly, the fact that highly magnified images do not have the same magnification. It has been observed actually many times, for example, most recently in this paper in a strongly lens system magnification of 140 or something like that, where they can see the two images basically shown here, just have about 10% flux anomaly. This is of course not the only explanation, but it's one possible explanation, and it will be good to actually firm up this kind of expectations. So this is all I'm going to say about astrophysical implications. And it applies when the dark matter is in the ultralight regime. I'm going to end with, due to the lack of time, I'm going to skip a whole bunch of slides. I apologize for that. Experimental implications. So some of you might not care so much about the ultralight, but how about just merely light? For example, QC the axion. In particular, in these slides, I'm going to show you numbers where the scalar field is of the order of 10 to the minus 6 electron volts, okay? And a lot of the experiments use either the coupling to photons, like so here. This little f now is basically the axion decay constant I talked about earlier. Or the coupling of the scalar field to basically fermions. Psi, for example, could be nucleons, quarks, electrons, and so on. These two are fairly generic coupling. And there's a whole host of basically experiments that make use of these couplings. And again, because of lack of time, I'm not going to go over them, each of these kind of sample experiments in detail. They are very good reviews, which I cite here on these experiments. Suffice to say, I just want to point out, each of these experiments measures slightly different things about the axions. For example, ADMX measured the power of the photon output in a cavity, out of a cavity, and so essentially measure phi square. There's a different experiment that measures phi dots. there are experiments that measure phi actually at two different locations based on rotational polarization. The experiments that measure the coupling to the fermions, essentially they measure a coupling of the axion to spin. Sigma is the spin. And they measure spatial gradient of the axion. They all measure slightly different things. And that's actually useful to keep in mind. Now, the main point I want to get across, there are a few of them. I'm going to use the same slide. First point is that the axion field phi is related to the wave function that we have been talking about so far, times this e to the IMT. So psi is basically a slowly varying function of space and time. And e to the IMT is called the fast variation. So pictorially, if I'm at a fixed location, which many of these experiments are, you have a detector at a fixed location, the time series of phi probably will look something like this. It has rapid oscillation on time scale of 10 to the minus 9 seconds. If you have 10 to the minus 6 electron volt axion, the coherent time scale, which is basically these slow modulation, is much longer. It's about 10 to the minus 3 seconds. And one should think of this axion experiment as measuring something like this. They are not measuring something like psi being a constant, which is actually kind of, at least in the traditional picture, that's what often people implicitly have in mind. That is just given by the local dark matter density, the average dark matter density. Really, what you have is this slow modulation, which again comes from superposition of waves with random phases. And the fact that you have superposition of waves with random phases suggests, in fact, it's probably useful to think of these measurements as measuring, or you should actually measure correlation functions. One example I show here, this correlation function of power coming out of the ADMX experiment, which is basically a 2-point function of phi square. And what is interesting, I want to just highlight it here, is that at large time separation, there is a characteristic t to the minus 3 power law decay. And that is one of those signatures that one could hope to capitalize on in a kind of pooling signal out of noisy data. One could even measure other correlation functions, maybe even space-time correlation functions, which are fun to think about. And let me also say at vortices where, again, the wave function vanishes, phi is 0. So some of these experiments will measure 0. But the gradient of phi is actually not 0. So some of these experiments would not measure 0 when you encounter a vortex, which is an interesting observation. And lastly, let me also emphasize this whole study of vortices suggests to us, in fact, there is something interesting in the phase of psi, and the phase of psi shows up in the phase of the oscillation of the axion phi, like so here, right? So this is the amplitude of psi, the wave function. The phase is the phase of oscillation of phi, and there is some interesting structure there, particularly if you have a vortex around, and it's interesting and fun to think about measurements that actually focus on extracting information on the phase, in addition, of course, on extracting information on the amplitude, which is what most of the existing experiments are about. Okay, I think I'm running out of time, so I'm going to end with just this slide. Again, this is just a reminder. We have been looking at what I call the wave regime, very light dark matter masses, less than 100 electron volts. As long as you are here, you have wave phenomenon, classical wave phenomenon. And basically, these are two manifestations. You have defects like vortex rings, and you have interference. And there are all kinds of signatures, astrophysical or experimental, that one could think about. And I'm going to stop here. Thank you for your attention.
Okay. So thank you very much. We're really running out of time. We have time maybe for 1 or 2 important questions from the audience. If there is, okay, there is a question. in the chat. Can you see the question?
Oh, let me see. Let me go off this stop sharing mode so that I can see. Sorry, I went over, way over. Let's see. Questions.
Oh, no.
I could not see the question.
No, there is no question here. So actually, I have a little curiosity. So is there some analog of these vortices for electromagnetic waves, since they're also, you know, a classical field with large occupation number, etc.?
Yes, with electromagnetic waves. Let's think about that. Well, my guess is probably no. I have to think about this. The reason is here, the phase actually is related to, again, the U1 phase associated with particle number conservation, right? Whereas for photons, we don't have that. So I'm guessing probably no, but I should think about that a little bit. Yeah, but that's a good question.
I mean, the obvious difference is that the mass is equal to 0, but otherwise, three photons are like two scalars to me. So
right. Okay. That's right. Yeah, exactly. Because the mass is 0, there's really no there's no barrier to basically creating or destroying photons. So,
but not if you take the free theory. For the free theory, the number is conserved also.
For free theory.
Yeah.
Okay. Okay. Yeah. So here probably the existence of the mass makes the vortices in some sense more robust here. That, for example, you know, you might wonder, you know, this Taylor expansion argument sounds very general, but you could also wonder, well, once I introduce interactions, for example, in this case, that's gravitational interactions, you might worry that it might completely change the picture. And here, probably we are a little bit protected precisely because we have a finite mass. Whereas in the case of photons, I'm guessing probably not. But again, I should think about that a little bit. That's a good question. Yeah.
Okay. So there is actually a question from the audience. You can read it in the chat.
Okay. I'm going to read to everybody. This is from Maria Benito. Can you please comment on the heating of tidal streams as an observational signature vortex rings? Don't know if this can be considered important. Okay, that's a great question. We actually thought a little bit about that. There is for sure effect on the heating of tidal streams, but it appears the main effect is not so much from an isolated vortex ring. More is because if you have just gravitational scatter from, let's imagine you have a globular cluster and it's going around in the Milky Way halo and there's a tidal stream. Usually it's very cold. Those stellar particles along the stream, it gravitationally scatter with substructure, light vortices, and get heated up. If you ask what is the effect of the scattering from just one vortex, it's a very small effect. So the heating can only be seen once you have many scattering. And once you are in the regime of many scattering, it's not so much actually specifically the effect of a vortex. Basically all the general interference, substructure, constructive, destructive interference, they all contribute to the heating. So the answer, I guess, to your question is yes, there is effect on the heating of stream, but it's more from kind of general interference substructure rather than specific to vortex rings. Although there is an interesting conceptual question, I think that needs to be clarified, which is that vortex rings, at least from what we can see, they can actually move in principle very fast. And the question is, what do these objects that can move very fast, what would they do? Could they actually do something otherwise you would not expect based on more general interference substructure? I think that remains to be clarified. Yeah. Thank you for asking.
Okay, I think we are really running out of time. So let's thank Lam again.
Thank you for your attention.
A very nice talk, and so we'll continue next week with more talks on Tuesday.
Thank you. Stay safe and healthy.
You too. Thank you.
Thank you.
Mm.